1 plus 2 is equal to 3, but also 4 plus 5 plus 6 is equal to 7 plus 8, and 9 plus 10 plus 11 plus 12 is equal to 13 plus 14 plus 15. And this pattern continues forever. Undulating numbers are numbers that alternate between two digits. For example, 14141 is an undulating number. Some prime numbers can be also undulating, like 131 or 74,747, which are both prime and undulating. Prime numbers that are also undulating always have odd numbers of digits and are not that uncommon. Square numbers are just whole numbers raised to the power of 2. For example, 11 squared is a square number. 11 squared is also an undulating number, because it is equal to 121. What's interesting is that we have only found 4 square numbers that are also undulating. The undulating cube numbers are even rarer. 7 cubed is the only undulating cube number we've found. This triangle with all sides measuring 1 has an area of approximately 0.43. Moving on to a square with a side length of 1, its area is exactly 1. Next we have a regular pentagon with a side length of 1, which has an area of around 1.72. As we increase the number of sides, the area of the regular polygons grows larger. A regular decagon already has an area of 7.69. By further increasing the number of sides, the polygons start resembling circles more closely. This is a regular pentagon with 1000 sides, each measuring 1. Its area is approximately 79,577, and its shape already looks like a circle. We can push this even further. A regular polygon with 1 million sides is massive and has an area of around 79 billion. Factorial is the product of all positive integers from 1 up to a given number. It is denoted by an exclamation mark. For example, 5 factorial is equal to 1 times 2 times 3 times 4 times 5, which is equal to 120. Factorions, on the other hand, are numbers which are equal to the sum of the factorials of their digits. For example, 145 is a factorion, because 1 factorial plus 4 factorial plus 5 factorial is equal to 145. Factorions are very rare. In fact, there only exist 4 of them. They are 1, 2, 145 and 40,585. 8 cubed is equal to 512. The sum of its digits is equal to 8. There are only a few numbers with this property. 17 cubed is equal to 4913, which has a sum of digits equal to 17. 18 also works. The next two are 26 and 27. We can also count 1 and 0, and that's it. These are all numbers with this property. Let's start summing the odd numbers. That is 1 plus 3 plus 5 plus 7 plus 9, and let's stop here. Now let's divide this sum by the sum of the next 5 odd numbers. The result is equal to 1/3. This always holds true, no matter how many odd numbers we add, as long as there is the same amount in the numerator and the denominator. The harmonic series is an infinite series formed by summing all positive unit fractions. That is 1 plus 1/2 plus 1/3 plus 1/4 and so on. After summing the first 10 terms of the sequence, we get around 2.93. After summing the first 1000 terms of the sequence, we get around 7.49. The sum of 1 million terms in the sequence is equal to around 14.4. We can see that this series is starting to slow down because the further we get, the smaller fractions we add. But surprisingly, this infinite sum diverges to infinity. It might not look like this, because even after 1 billion terms, the sum is equal to only around 21.3. But to prove it, let's look at a different sequence. The first term is equal to 1, and the second is equal to 1/2. The next two are equal to 1/4. The next 4 are equal to 1/8. And this pattern continues. By grouping the equal terms, we can see that this series is an infinite sum of 1/2, so it's equal to infinity. We can also see that each term of the harmonic series is greater than or equal to the corresponding term of the second series. So it means that the harmonic series also diverges to infinity. Now let's remove every term that contains at least 1 9 from the sequence. Although the sequence still has an infinite number of terms, it no longer diverges to infinity. Instead, it converges to a finite limit, which is approximately 22.92. This would also occur if we remove terms containing the digit 7 or 3, or any other digit, or even if we remove terms that contain a specific sequence of numbers. To understand why this happens, let's look at this problem from a different perspective. Let's see what percentage of integers contain at least 1 9. If we look at the first 10 integers, only one of them contains a 9. However, as we examine larger sets of numbers, the percentage increases significantly. For example, in the first 100 integers, 19 of them contain at least one digit 9. In the first 1000 integers, more than 27% of them contain at least one 9. As we continue to analyze bigger and bigger numbers, the percentage of numbers containing at least one 9 approaches 100%. This is because with larger numbers that have more digits, it becomes increasingly difficult to find numbers that don't contain any 9s. N of these digits can potentially be a 9, and the chance that we get a 9 in at least one of those digits is very high. Newcomb's paradox is a thought experiment created by William Newcomb. It was first analyzed in a philosophy paper by Robert Nozick in 1969. In his article, Nozick noted that, to almost everyone, it is perfectly clear and obvious what should be done. The difficulty is that these people seem to divide almost evenly on the problem, with large numbers thinking that the opposite half is just being silly. The problem goes like this. There are two boxes and a reliable predictor. You are given a choice. You can either take only box B or take both boxes. In box A, there is $1,000. The content of box B was set by the predictor before you made your choice. If the predictor has predicted that you will take both boxes, then box B contains nothing. If the predictor has predicted that you will take only box B, then box B contains $1 million. The predictor can make highly accurate decisions, but he already made his move before you made your choice, and it cannot be changed. So, what would you choose?